So it's my pleasure to invite Josh Grochow, sorry, to give a talk today. So he'll be giving two talks, overview of GCT as well as some of his work, I hope. So yeah, so Josh, you can start. Yeah, thanks.
Great. Yeah, thank you very much for inviting me. It's been a great lecture series so far, and I'm very excited to be here to be able to tell you all some things that I've learned, and yeah, I look forward to subsequent lectures. So the plan for the two lectures, actually, as KV said, so I will cover some things from the paper GCT1 and some of my own work and some other observations. And so the real plan for the two lectures is, so today, so lecture one. So we're going to start with getting a bit more, let's say, concrete feel for what representations in coordinate rings really look like. Just in a few small examples, but examples that at least when I saw them really clarified a lot of things for me. And this will lead us through some of the examples to this notion of partial stability. That's a generalization of the notion of stability from geometric invariant theory that was defined by Momoli and Sahoni in GCT1. And then we'll talk a little bit, we'll do some examples, we'll talk a little bit about sort of why partial stability might be important. And this is one of these things that actually I'm very glad to have the opportunity to highlight here, because I think it was in GCT1, it plays some role in GCT2 and some of their other papers, but that I think it has a much further role to play in continuing this line of research. And so hopefully some people will have some ideas of things to do with it. And then this will lead us to sort of the importance of the symmetry groups of the points being considered. And so then in lecture 2, we'll talk about characterization by symmetries, also from GCT1 and 2. And we'll talk about how this is related. I think was mentioned a couple of times, this natural proofs barrier. And then finally, we'll talk about P versus NP in GCT. So here, I mean actual P versus NP, not permanent versus determinant, not algebraic, actual P versus NP. And so, yeah, I guess natural proofs barrier, I mean, I'll give the exact references next time, but that's Razvarov Rudich, but the rest of this will mostly be, the main ideas are in GCT1 and 2. Okay, so, yes, let's start with at the beginning here. So one of the things that I wanted to talk about, Christian in his first lecture talked about, okay, we're looking for, some polynomial that vanishes on some orbit closure and not on some other point. So if you want to prove, say the permanent is not in the orbit closure of the iterated matrix multiplication polynomial, right, then the goal was find polynomial f whose restriction to this orbit closure was 0, but where when it's evaluated on the coefficient vector of the permanent, it's non-zero. And then from there, he actually started with, okay, you just want a function. Any function that does this will work. But in fact, you can make that function continuous. You can make it a polynomial. And you can make it have something to do with representation theory. And I kind of want to come at it from the opposite direction, is let's start with representations in the coordinate ring and see what they're telling us. So again, in that first lecture, Christian gave the very nice example of if you're looking at the space of homogeneous degree 2 polynomials, in 2 variables. So this is, a x squared plus b xy plus c y squared for all a, b, and c. That you can look at the polynomial b squared minus 4ac. This is invariant under the natural SL2 action here. So this is SL2 acts by change of coordinates on x and y. So this is A acting on xy is a11x plus a12y, a21x plus a22y. Okay, and then if you wanted to act on the degree 2 polynomials, you just plug these into your degree 2 polynomial. But if you do that, as long as a has determinant 1, b squared minus 4ac will not change. And b squared minus 4ac tells us something. So being 0, this happens if and only if a squared plus bxy plus cy squared is a perfect square. And in the context of complexity, we would say this is Waring rank 1. Okay, so this is a very nice example, but this is a single invariant polynomial. So in terms of the representation theory, this polynomial is sort of very simple. So if we look at the span, the one-dimensional span, so this sits inside degree 2 polynomials on degree 2 polynomials in 2 variables. So there are lots of 2's floating around here. So let's say which is which. So the 2 variables corresponds to this 2. The fact that we're doing the space of degree 2 polynomials. So this 2 is this 2. And then b squared minus 4ac itself is degree 2. And that's this 2. Okay. So this span, this is a trivial representation of SL2. Okay, but in general, in GCT, we want to look at other representations in these coordinate rings. And the question is, what do those correspond to? What are those telling us? Okay, and so I want to give you some more examples here. And in general, the message here is a G representation let's say V in the coordinate ring corresponds to a G invariant property. Okay, where here, the point is that, sure, if you have a single polynomial that's invariant, then its vanishing certainly, the set of points where it vanishes certainly is G invariant. But also, if you have a whole set of polynomials where as a set, those polynomials are G invariant, meaning it's a G representation. So anything in this set, when you act by G, goes back into this set. If you ask for all of those polynomials to vanish, the set of points where all of those polynomials vanish will be G invariant. Okay. And so, yeah, let me just say that a little more slowly and write it out, and then we'll do some more examples. So, right, so V as above. And now let's consider the vanishing locus of V. So this is the set of points in our space, whatever our space is, whether it's homogeneous polynomials or matrices or tensors or what have you, where f of x is 0 for all f in our G representation. Okay, and the claim, which I guess is the down arrow in the above correspondence, is Z of V is, now here the notation is somewhat confusing. You might say closed under G, but note, like careful, this is closed under the action of G. This is not necessarily Zariski closed. So, okay, that's not the best choice of nomenclature because it conflicts with Zariski closed. Or we might say this is G invariant, but this means setwise, not pointwise. So, okay, this is also maybe not the best choice of notation, of nomenclature, but these are the only two names I know for this. And so you kind of have to pick your poison. Right, so what this means is more specifically, i.e. X is in ZV if and only if GX is in ZV for all G in G. And how do we prove this claim? So suppose X is in ZV, consider GX. And now, what do we want to know? We want to know that every polynomial in our G representation vanishes on GX. So let F be any polynomial in V. And the question is, what is F of GX? Well, by definition, this is G inverse acting on F on X. This is by definition of the action on polynomials. Okay, but V is closed under the action of G. So G inverse F is also in V, which means G inverse F evaluated at X is 0 because X was in ZV. Okay, but we just said that that was F of GX. Okay, so every f also vanishes at gx, and therefore gx is also in zv. So that proves the claim that's in one direction. And then in the other direction, sorry, I should have been a little more careful. So this, let's see. Oh yeah, sorry. Yes, good. I phrased it the way I wanted to. Okay, so in the other direction, we have to be a little more careful about, okay, what do we mean by property? Well, maybe what we should really say is a G invariant Zariski closed set, right? Because if we're talking about the vanishing of polynomials, we're only ever going to get Zariski closed sets. So in particular, we want this to be Zariski closed set, or an algebraic variety. Okay. So let's see the other direction here. So now we want to say, sorry. All right, so now we want to say, let Z be a G invariant Zariski closed set. And to be specific, i.e. this means X is in Z if and only if Gx is in Z for all G. Okay, and our claim is now there exists a G representation B such that Z is the zero locus of V. One thing to note here, and this was the thing I was worried about being careful about before, I just said a representation. It doesn't have to be irreducible. And in general, it, like for this correspondence, the way I phrased it here, this won't be irreducible. It could consist of many irreducible components. Okay. So let's look at the proof. So first we say let I be the ideal of our Zariski closed set. One thing to note, because our Zariski closed set is closed under G, that I is closed under G. So first, I is closed under G. Why? Well, the proof is basically the same as this proof, except now instead of fixing an X in here and looking at all F in V, we do the opposite. We look at a particular F in V and we look at all X in here. Okay, but then the formulas are the same. So let's say Y. So let F be an I. Consider GF. Oh, sorry, I got my quantifiers backwards. The quantifiers are the same. The order in which you do things is different. Okay, so consider GF. We want to show that GF is an I. So GF will be an I if and only if GF evaluated at X is 0 for all X in our Zariski closed set. Okay, but this is F of G inverse X. Okay, but G inverse X is in our Zariski closed set. So G inverse X in Z implies that this is 0. Okay. All right, then the second thing, as has been mentioned in some previous lectures, because we're in geometric situations, the ideal is finitely generated. So I is finitely generated. This is Hilbert's basis theorem, or one of Hilbert's basis theorems. There are at least 2, maybe 3 theorems with that name. So let's say I is generated by some f1 up to fk. And now what we'll do is we'll take these finite generators and we'll just hit them with G. Okay, and a theorem that had been mentioned before is that when G is reductive and you hit a generator with G, you always get a finite dimensional thing, even if your group is infinite, and even though we're in an infinite polynomial ring. Oh, sorry, I don't even need reductive. I think just if G is an algebraic group, that's enough here. Okay, so V is now going to be the span of G acting on Fi for all G and G and for all of our generators. Okay, and now the point is, okay, F is now a G module. The generators of our ideal are contained in V. So Z is Z of I is Z of our generators. In general, what we now know is this contains Z of V, but because of this first part where I is closed under G, we in fact know that V is also contained in I. Okay, but these two are equal. So Z of V is the same thing. All right, so this is sort of the general theorem, and this is the main message, that like, what are we looking at when we're looking at the vanishing of G modules in the coordinate ring? We're really looking at G invariant properties, G invariant Zariski closed sets. Okay, but now let's see some more examples. And for this, I actually want to come back to another example that was mentioned in an early lecture, I think when they were first covering like group actions, which is graph isomorphism. Okay, and this will be, I guess you could think of this as sort of a GCT approach to graph isomorphism. It's something that I talked about when I gave lectures on this in Toronto, I don't know, almost 10 years ago now. I think there may be lots of interesting questions here, but it's also a nice little example. So this is sort of a GCT style approach to graph isomorphism. And for simplicity of the math, just to see this example, like let's look at 3 vertex graphs. Okay, so we know the answer, right? But we don't know the representation theory yet. So consider 3 vertex graphs. And here we'll also do directed, and we'll allow self loops. Okay, so we really have any 3 by 3 0, 1 matrix as our adjacency matrix. And what does it mean if I have 2 adjacency matrices? What does it mean for 2 graphs to be isomorphic? Well, the rows are indexed by the vertices, V1, V2, V3. The columns are indexed by the same vertices. And an isomorphism is permuting the vertices. So this is, you conjugate by a permutation matrix. So maybe let me say this. So two graphs, G isomorphic to H. And now I guess if you're following along, I think this was an exercise from a previous lecture. So if you haven't done that yet, you should go do that. So if and only if there exists a permutation matrix, say pi, such that when I conjugate the adjacency matrix of G by pi, I get the adjacency matrix of H. Okay, so in our example, so for 3 vertex graphs, we're looking at S3. And the nice thing about S3 is that its representations are particularly simple. So I can tell you all of them. And they're things that more or less, even if you haven't seen representation theory, you've probably seen these before. So for 3 vertex graphs, we're dealing with S3. Okay, and what are the irreducible representations of S3? Well, there's the trivial representation in which everything acts by the identity. There's the sign representation. So this is still a one-dimensional thing, but now transpositions act by -1. So this is the identity, and 3 cycles go to 1, and 2 cycles go to -1. And then I guess I would call this a dihedral representation. There's the symmetries of the triangle in the plane. So think of an equilateral triangle placed at the origin. Okay, and think of rigid motions you can do to the plane, including reflections that send the triangle to itself. Right, so I can rotate by 120 degrees. That corresponds to my 3 cycles, or I can flip around any of the 3 axes of the triangle. Those correspond to the 2 cycles. Okay. So these are all the irreps of S3. And now what is the space we're acting on? Well, what is this action in terms of representations? So first of all, what's the action even just on permuting these things? It's none of these things, right? So the natural action of S3 on C3 just by permuting coordinates. It turns out that this is a copy of the trivial representation and the dihedral representation. Okay, and how can you see that? Well, what's the trivial representation? The trivial representation in here, if the EI are the standard basis vectors, if I take the sum of these 3, okay, when I permute 1, 2, and 3, this is sent to itself no matter how I permute them. So this is my trivial representation. And over here, this is, if you like, the set of vectors V. It should be orthogonal to that, where V1 plus V2 plus V3 is 0. Okay. And essentially, what's happening here is that if you take the natural action on S3, on C3, and you project the basis vectors down into this space, you get 3 vectors that sum to 0, and it's the 3 corners of this equilateral triangle. Okay, so that was not a full proof, but that's sort of a sketch, and hopefully it was at least a little bit convincing. Okay, and now the question is, what is this action on graphs? So action of, and this part we could say for Sn on n vertex graphs. So we say, let's say, let V be the natural action by permuting the n coordinates. Well, what's happening here, instead of inverse, I could also have said transpose, because for permutation matrices, inverse and transpose are the same thing. And transpose really just means we exchange rows for columns, but that otherwise it looks the same. And so this action as a representation is really V tensor V, where you can think of this as rows and you can think of this as columns. So if just as spaces, this is a space of n by n matrices, but now we're also paying attention to the action on Sn. And the point is that whatever permutation you have, it acts on the rows the same way as it acts on the columns. And actually, I claim this notation makes that clear, right? It's acting in the same way here and here. I didn't say this is some different representation. And if you go back to the definition, rather than our notation here, that's what we said, right? We said we want Sn to permute the rows the same as it permutes the columns, because it's permuting the vertices in both cases. And this transpose, this was like an artifact of our matrix notation, where we said, okay, how do we get the notation to work out so that it permutes the rows the same as the columns? Well, if you work through it, you need a transpose here, but really it's the same action on the rows and the columns. Okay. If you like, this is also here because this is on the right, but it's still a left action. That's another, if you've seen that sort of thing, but okay. Now, okay, now back to S3. So we can see what things look like. Oh, right. So sorry. First, what's sort of our general approach? So our general approach will be, okay, now instead of separating orbit closures, we're separating, orbit closure, instead of separating orbit closures that correspond to complexity classes, we're now separating orbits that correspond to isomorphism types of graphs from one another. So I'm proving, I'm using this approach to try and prove that two graphs are isomorphic or not isomorphic. Okay. So what's the idea? The idea is we look at the coordinate ring of this space. Which in this case will be a polynomial ring in the n squared variables xij, which are just the entries of our matrix. And I want to look at it as an Sn representation. And given two graphs, I can now ask in here, so given GH, try to show G is not isomorphic to H by finding an irrep in here that vanishes on G, but not H. Okay, and by our general correspondence, what does this really say? This is really saying, find an Sn invariant property, i.e. Sn invariant property that G has, but H doesn't. Okay, but what does Sn invariant here mean? This is the same as saying isomorphism invariant. Okay, and even further, if you wanted to go even further, instead of finding one, which we would call a polynomial obstruction, or okay, we don't quite have highest weight vectors here, but this is like the highest weight vector obstructions of Bergeser and Eigenmeier. Instead, you could ask for multiplicity obstructions, or you could say, find me an isomorphism type of these that vanish, where more of them vanish on G than vanish on H. I kind of don't want to get into that because I don't have much more to say about that. But I want to give you a feel again for, okay, how do these things arise? And what do multiplicity obstructions, like what could they even look like in this situation? Okay, all right, so this is sort of the GCT approach to proving graphs are not isomorphic, or I should say a GCT approach. Okay, and in general for Sn, if you look at this, and you ask about the degree D component of this, and you try and decompose that into irreps, that's closely related to like classical hard problems in representation theory, as with, you know, sort of almost everything in GCT. Okay, but in the case of S3, we can do it. And let's see, like, what do these things look like, even in degree 1? Okay, so let's go back now. So back now to 3 vertex graphs. Okay, and let's consider degree 1 in here. Okay, so what is this? This is 9-dimensional, right? And we said we have 3 irreps. We have a trivial, we have a sine, and we have the dihedral, which is 2-dimensional. Okay, and I claim to you, after a little bit of calculation, that there are 2 trivial reps, and I'll tell you what they are, 1 sine rep, and 3 dihedral reps in here. Okay, and do these dimensions add up? This is 2 1-dimensional things, 1 1-dimensional thing, and 3 2-dimensional things. So 3 times 2 is 6, plus 3 is 9. So that's it. That's all the degree 1 stuff. And what are these polynomials? So 1 trivial rep here is, if I think of these as matrices, is the trace. So this is, you know, x11 plus x22 plus x33. Okay, great. So that's an invariant. We've seen those before. What does this one correspond to? This one corresponds to, this vanishes on graphs. If our graphs are 0, 1 adjacency matrices, this vanishing means there are no self loops. That's the invariant property that this corresponds to, right? So vanishes on graphs, meaning 0, 1 matrices, if and only if no self loops. Okay. The sign representation. Okay, there's another trivial rep, which is like the sum of all the entries of the matrix, which vanishes if and only if there are no edges. Okay. Notice, by the way, that those two, like, you can also take sums and differences of them, right? This was a thing that was mentioned a few times. Within an isotypic component, decomposition is not unique. So you could also look at the sum of the non-diagonal entries, right? That's another invariant, but it's in the span of those first 2. Okay, all right. Let's see. Oh yeah, KV, one question. How long should I go? It was a little unclear from previous ones.
75 minutes, I mean, is the time, but some people have gone on. So yeah. So,
okay, perfect,
yeah.
Perfect,
Yeah.
Great. Yeah, that's what I was planning on. Yeah.
Yeah.
Okay, all right. Yeah, so let's see this sign rep. And I have it written down here. Where did it go? Yeah, all right, so the sign rep, turns out, is this guy, x12 plus x23 plus x31 minus x21 plus x13 plus x32. Okay, so if this vanishes, what does this say? This says, if you look at these 3, these are 3 edges oriented coherently, 1 to 2, 2 to 3, 3 to 1. So this is like a directed cycle. So this vanishes if and only if there's one, like, if the presence of one directed cycle is the same as the presence of the other directed cycle. So this vanishes if and only if 1, 2, 3 present, if and only if the backward cycle is present. Okay. And so first, the one thing I want to highlight here, okay, this is still a 1-dimensional representation, so there's only one polynomial here. But already, hopefully, this gives you some feel of, like, this was a different representation. It feels different, right? These ones, they're really just invariant. Like, either a graph has self loops or it doesn't. this one, there's something about orientation happening, right? And so that should sort of jibe with your general feeling of signs of permutations, right? So I want to start to get a feel for what does it mean for non-isomorphic G modules in the coordinate ring? Like, what do they look like? Why does the isomorphism type of a G module matter? Okay, and we start to see here that it corresponds to a different kind of property. Okay, and now let's do the dihedral ones, and we'll see even more, because now these are things that they have more than one polynomial in them that spans them. Okay, and here they get a bit more complicated, but and actually it took some time because it's sort of harder to calculate the decomposition. But yeah, let me just tell you what they are. So these dihedral ones, so one of them is spanned, it's the span of the following three things. 2x11 minus x22 minus x33, and all three permutations of this. Which, you know, it had to have all three permutations of this because it's closed under the action, oops, of G. Okay, first, let's just check, like, how do I know this is dihedral rep? Well, if I look at the action of Sn, it's sort of clear, you know, these things are determined by which thing has coefficient 2. It's either 1, 2, or 3. If I permute by any permutation, it just swaps these three around. So that looks like the natural representation, but the sum of these three is 0, right? I have 2x11 minus x11 minus x11. So these are maybe not geometrically if you had to, like, if you pay attention to an inner product, but at least algebraically, these are like the corners of our equilateral triangle. Okay, and this rep, what is this vanishing tell? So this is really two-dimensional, right? I wrote down these three because it's like a very nice symmetric basis. You can see the action, but it's really only two-dimensional because the sum of these three things is 0. Okay, what does this representation vanishing tell us? Well, okay, on general matrices, I don't know, it's some complicated thing, but on 0, 1 matrices, it's not so complicated. This says if x11 is present, for this to vanish, x22 and x33 must both be present. And same for each of these. So this one vanishing, this one vanishes if and only if the existence of a self loop is equivalent to all self loops. Okay. All right, so that's one of our dihedral representations. And the other ones, so I can write down for you, I'll write down for you what one of the generators is, just so you can see it. It sort of looks like this one, but I don't want to get too much into it because the interpretation is more complicated. And so let's see, we have this minus x23 minus x31 plus 2x21 minus x13 minus x32. So it's generated by this, and then you hit it with all permutations. And one thing to notice is, you know, again, these three are oriented, these three indices are oriented coherently in a cycle, 1 to 2 to 3 to 1. These are the opposite cycle. If I swap 1 and 2, I swap these cycles. And if I permute within a cycle, I stay within a cycle. And then there are two other things, and the picture looks kind of like this picture, but with two other things. And what is this vanishing? Well, again, on 0, 1 matrices, okay, it's a little tricky, but what this tells you is the number of edges between 1 and 2 in either direction is equal to the number of edges between this you have to write down the polynomials and you have to sort of work through the case analysis for 0, 1 matrices, but this is what it corresponds. This is what this module vanishing corresponds to. Right? So one thing here is there's no one invariant polynomial whose vanishing tells you this property. Okay, so we really needed this module. Okay, and also note this condition, it has a very similar feel to this condition. And I claim that feel is made precise by the fact that these two modules are abstractly isomorphic as G modules. Okay, and so this is the feeling that I want to start to get to of what does it mean for two G modules in the coordinate ring to be abstractly isomorphic as G modules. And when we talk about there being more of one type of G module, what does that mean? Okay, all right, so this ends my thing for graphs. All right, and now I want to do one more, and then maybe I'll pause for questions. So one more example. So let's consider now the action of GLN cross GLN on n by n matrices, where AB acts on X by left and right multiplication. And again, this transposes here just because I want this to be a left action. Okay, so recall that orbits here are completely determined by rank. Meaning X is in the same, so X equals G dot Y, if and only if, so there exists G such that X equals G dot Y, if and only if they have the same rank. Right, and this is because when you can do row operations and column operations, you can always make it diagonal with zeros and ones on the diagonal. Okay, but if we look at the invariant theory, sort of in the style of classical invariant theory or geometric invariant theory, there's one invariant here. So the invariant ring is C adjoin the determinant, meaning there's only one invariant, which is the determinant of X. So invariants, they sort of capture rank. They will tell you whether it's full rank or not, but not beyond that. So one thing is the set of singular matrices, so the set of X such that rank of X is not full, this is the null cone, right? We said we had one invariant determinant. Where does it vanish? Well, the things of not full rank. Okay, and yet we mathematicians, we have an invariant that separates orbits here, namely rank. Okay, but it's not a polynomial invariant. Okay, but it is still a G invariant, which means by our general correspondence, there should be some G modules in the coordinate ring that it corresponds to. And we know what those are, right? So the set of X such that rank of X is at most R. This is a Zariski closed set, right? Hopefully you saw this in some linear algebra class, but if not, then just take this on faith. So this is the zero locus of all R by R minors of X. So you take any R rows, any R columns, you get an R by R submatrix, you take that R by R determinant. Okay, you look at all of those, their zero locus is the set of matrices of rank R. Okay, and my claim is that the span of the R by R minors is a G representation. In fact, this would often be written as wedge R V tensor wedge R W if our original space was V tensor W. So n by n matrices V tensor W, and we have our group GLV cross GLW acting. All right, and so this this notation, okay, if you, I think maybe Luke talked a little bit about this, but if you don't remember, or if you don't know what it means, you can just take this as abstract notation for what this is. But this tells you the isomorphism type of this representation. Okay, and so the point is, here I have these modules sitting inside the coordinate ring, right? So our coordinate ring again is so C of V tensor W. This is just C adjoin all Xij. Right? Okay. And these modules all sit inside here, and their vanishing corresponds to this. And I can use their vanishing or non-vanishing to distinguish orbits. Right? So X, Y are in the same orbit. And here, note, so just from the notation, hopefully the notation makes clear, when I change this index, that's changing the isomorphism type of this representation. So X, Y are in the same orbit if and only if the set of R such that the R by R minors vanish on X. So that tells me the rank. This should be the same as the set of R such that the R by R minors vanish on Y. Okay. All right, and I claim what's going on here. So in the null cone, you have things that look like this. And I claim that actually this is very analogous to what's happening in the permanent versus determinant situation, or permanent versus iterated matrix multiplication, where you have permanent on a small number of variables sitting inside a space with a large number of variables. Okay. Where the fact that this permanent doesn't depend on all the variables is like somehow related to the fact that these zeros are here. Okay, and this will lead us to this notion of partial stability from GCT1. But I think maybe I want to take a moment to pause and see if there are questions.
I have a question. When you do these group actions in GCT, you can consider the action on the coordinate ring, or I guess on the ideal of a variety. Is there a good reason to choose between the two?
Oh, yes, but there are good reasons to choose both, I think, is the answer. Okay. So the ideal and this is just my personal opinion. Maybe some of the algebraic geometers who are involved in this have deeper thoughts on this. But I would say, okay, the ideal is nice because you get to think about, what's vanishing. Okay, and the coordinate rings are nice because they're rings, and so maps between them are ring homomorphisms. I don't know, you can talk about their structure as rings, right? And I guess those are sort of the starting points. I mean, I think probably a lot more can be said. Like information theoretically, you're of course right, Pascal, that like if you knew the information of one, you would know the information of the other, right? They're sort of the same from an information theoretic point of view. But from an algebraic point of view, right, they're sort of dual. I guess one other thing is that the ideal depends on the embedding and the embedding into a space. And the coordinate ring gives you the abstract isomorphism type of the G variety.
Okay.
However, you can sort of recover the ideal because you can do this natural thing where you embed the G variety back into a space and then you find the ideal again. And, so I guess that maybe the coordinate ring is slightly more intrinsic, but also when we're separating these orbit closures, we care about how they're embedded in space, right?
Yes.
So, okay. Yeah, I guess it's good to be able to go back and forth. At the very least, it's good to be able to go back and forth because some authors prefer one and some authors prefer the other. So you should get used to both. And of course, the confusing thing is when you talk about multiplicity obstructions, the inequalities go like the opposite way, depending on whether you're using the ideal or the coordinate ring. Yeah.
Okay, thank you.
Usually the ideal is also difficult to get hold of. That's probably the hard part of this also anyway. I don't know if that also is, I mean, coordinate rings are, at least you're talking of functions on that object and so on. So it's probably more amenable. I don't know. I don't know whether, I never asked this question to myself, but.
Right.
Question, yeah.
Yeah, maybe we can talk more after, because like I said, I think there may be lots of things to say here. But okay, other questions? Okay.
So isomorphism, graph isomorphism. This way of looking at this. I mean, how far can you push it? Can you push it beyond? As in. So even in the three words,
so one thing we know in the case of graph isomorphism, because the group that's acting is finite, we know that in fact orbits can be separated by invariants.
Correct.
Because all orbits are closed because they're finite sets.
Correct.
Okay. So the question here would be, okay, by looking not just at invariants but at other representations, can you separate orbits, i.e., can you tell if two graphs are isomorphic in, say, lower degree than if you were only using invariants? Right. So with invariants, you might need invariants of very high degree, which computationally would be bad. And the question is, if you use other representations, can you do it in lower degree? And I don't know the answer. And as far as I know, basically anything, this hasn't really been explored, and so basically anything you can ask about this approach to graph isomorphism is open and interesting, and I'm very happy to talk about it with whoever wants. Yeah. Okay. All right.
Maybe further to that point, could I ask one quick thing?
Yeah.
Is there a way to automate coming up with these basis vectors that you found, or was that just staring at it long enough and sort of ad hoc?
Yeah. Okay. So in the case of
representation.
Yeah. No, you definitely can. So from the representations, you can build these projection operators, and then you basically start hitting random monomials with projection operators, and those will give you things in the isotypic component. And then within the isotypic component, actually there, I believe there is an algorithm, but I don't know it off the top of my head. And so they're like splitting up the 3 dihedral representations from one another. That was kind of just me playing around by hand till I got it to work. I think there is an algorithm, but I didn't know it offhand when I was preparing the talk. So yeah, but the other part, projecting into an isotypic component, that's like sort of classical reductive representation theory.
Okay, thanks.
Yeah. Okay. All right. Oh, Somnath. Okay, good. Let's talk about that after. Yeah, because I want to get to partial stability here. Okay. All right. So, right, one issue here in this case was we could separate this by invariants, general invariants, not the invariant ring, not polynomial invariants, but invariants, which means G modules in the coordinate ring. But anything other than full rank versus not full rank, you know, all the non-full rank things were in the null cone. So from sort of a GIT perspective, that seems bad, right? All the things you're interested in are in the null cone. And a similar thing happens in GCT, where you know, you're trying to write permanent as a projection of, say, a larger determinant or a larger iterated matrix multiplication. And that permanent is not going to depend on all the variables that your iterated matrix multiplication started out as. And so it will also be in the null cone. Okay, but you want to say it's still somehow nice that, like, when you looked at the permanent just on the variables that it corresponded to, that it was very nice. It was in fact stable in the sense of GIT. And so that should somehow be reflected even when you embed it in this larger space. And so this is where the idea of partial stability comes from. So this is partial stability. Okay. And this is from this GCT1 paper by Momoli and Sahoni. Okay. And let me pull up the definition. So, okay, this is the idea. This is sort of the problem. At least this is retroactive history here. This is, I looked at the definition of partial stability and it's like, what problem is this trying to solve? And they have many comments on why it's useful, but it seems to me like this must have been what they were dealing with when they were sort of forced to discover this notion. Okay, so what's the idea here? The idea is, so right, first, let me just recall something about stability. So stable, in this case, we'll say X is stable, means that the orbit is closed. And sometimes people also require that the stabilizer is finite, but for now, we're not going to do that. We'll just say stable points mean the orbit is closed. Okay. And I guess we're excluding the zero orbit, right? It should also not be in the null cone, sort of by fiat, but if you're in projective space, then you're fine. Okay. Okay, and one of the things, so there's a theorem that I guess goes by the name of Matsushima's criteria, but was proved in various levels of generality by various people, that says this means that the stabilizer of X is reductive. Sorry, I should have one direction here. The other direction tells you it's affine, but not necessarily that it's closed in the given embedding. Okay, and that's nice because we like reductive groups, right? We can talk about their representation theory and multiplicities and so on. All right, so now what is this notion of partial stability? So the definition, okay, and I'm going to write the definition as they wrote it because there are surely subtleties here that I'm missing, and then I'll talk about some examples and sort of my maybe more naive way of thinking about it. Okay, so we say point in projective space is partially stable. And remember, these are like the examples to keep in mind, in particular this one, but we'll see also this one. So it's partially stable if three things. So there exists a maximal parabolic subgroup of G. Okay, and what does this look like? So there's a general definition of parabolic group, but the picture you should have in your head of GLN is block matrices like this. Okay, with the following properties. Let's see, a maximal parabolic containing the stabilizer. Such that three things. H, the stable, let me give the stabilizer, I'll continue to call it the stabilizer. Okay, the stabilizer contains R, where R here is, if this is our parabolic group, R here is this. Okay, technically this is called the unipotent radical. Okay, but you should think of it, particularly in the case of GLN, it literally is this. Okay. 2, this point is actually stable, but with respect to a smaller group, with respect to some group K contained in the diagonal part here. So this is called a Levy subgroup. Okay, and I'm giving you the names because you'll see the names in literature and they apply more generally, but I'm also giving you the picture because this is the picture in GLN. Like this is what the Levy subgroup looks like. K, where K is not much smaller than L. So stable with respect to K, where K is reductive. And the rank of K is allowed to be smaller than the rank of our Levy subgroup by some defect delta, okay, which will often be 1. Okay, and the stabilizer of X in L should also be reductive. And finally, the L orbit of X, which is isomorphic to L mod the stabilizer in L of X, is not too small relative to the G orbit of X. Okay, and more precisely, we can say the dimension of the L orbit over the dimension of the G orbit is at least some delta, or this is another parameter. Okay. All right, so this is the definition. So a remark, when the parabolic subgroup is actually equal to the whole group and the defect delta is 0 and this ratio capital delta is 1, this is the same thing as stable. So there are lots of things here, but in the stable case, all of these things hold with defect 0 and this ratio being 1. Okay, and they hold kind of trivially because the point is this K will then just be the original stabilizer of X that you started with. Okay, this Levy subgroup will be the whole group. Okay, this unipotent radical will be the trivial group. And here like this will be G mod the stabilizer of G, it will be the same orbit, so delta will be 1. Okay. So in the case of stable, so in the case of stable, a lot of these things sort of become trivial in some sense. But remember, the whole point is that if we allow these 2 bits of slack, we can handle examples like this. And this point, even in this big space, becomes partially stable, even though it's in the null cone. So partial stability lets us refine, gives us refined information about the null cone. So the message is, okay, so I guess I should say partial stability, and in particular, these 2 parameters refine information within the null cone. Okay, and in particular, partially stable points with delta, small defect, and this ratio close to 1 are very nice points in the null cone. That they are somehow different from arbitrary points in the null cone. Okay, and nice in a variety of ways. So hang on, let's see, I'm almost out of time.
We could take some more time. I mean,
yeah, I'm trying to see where in my notes, where is a good time to break between now and the next one. Yeah, okay, so maybe what I will do is I'll illustrate this notion of partially stable on matrices with rank. And then next time I'll start by talking about some of the nice things that partial stability gives us. Does that sound good, KB?
yeah.
Oh, great. All right. Okay. And by the way, one thing I will mention, even before I get to the example, is here, this issue of partial stability and the fact that the permanent only depends on a small number of variables, this is an issue regardless of whether you have padding or not. So, you know, we saw in some previous lectures, people had mentioned, oh, padding causes these issues. It's better to use iterated matrix multiplication because you don't need padding. That's true. But even when you get around those issues, you still have this issue that the permanent just doesn't depend on all the variables in the space. And so it's in the null cone. And so you still are going to have to deal with that somehow. And partial stability may be one way that's sort of an entry point for dealing with that. That seems to get us lots of nice things. Okay. But just for the last few minutes, let me come back to this example of matrices. So this is the left-right action. Okay. And we said that all matrices of non-full rank are in the null cone. But now what I want to show to you is just illustrate this definition and say, in fact, they're all partially stable. And the lower the rank is, the worse these parameters get. So as you get lower in the rank, you're sort of getting deeper into the null cone and you're getting like worse and worse points. So high rank, but singular matrices are in the null cone, but they're somehow nice. They're much nicer points in the null cone. Okay, so to do this, one of the things we needed is we really need to understand what is the stabilizer of a point, right? This was crucial. So let's see. So what is the stabilizer in this action of a point? And we said we can always make our points look like an identity matrix. We can always make our points look like this. So stabilizer of this. Okay. And so what is that? So I'm going to break up my A into blocks that are consistent with these blocks. And similarly, my B. Okay, and if you work out what happens, okay, what happens here? So this gives me the first column, A11, A21, 0, 0. Okay, and then when I multiply, I then get A11, B11 transpose, A11, B21 transpose, A21, B11 transpose, and A21, B21 transpose. Okay, and I want this to equal my original matrix, right? Because it should be in the stabilizer. Okay, so what does this tell us? Well, if we look here, this tells us that A11 and B11 are invertible. So the 1, 1 entry tells us A11, B11, maybe I should just say B11 transpose is A11 inverse. So they're both invertible. Okay, if I look at the off diagonal entries, the fact that A11 and B11 are invertible, but these things are 0, tells me that A21 and B21 are both 0. Okay, and then that's enough to force this to be 0. Okay, so what does my stabilizer look like? So my stabilizer looks like pairs A11, A21 is 0, A12, A22. So a pair. Okay, this is A11 inverse transpose, B21 is 0, B22 is whatever it is, and B12 is whatever it is. Okay, so this is my stabilizer. Notice it has this block form, right? So it has this block, exactly this block form with these upper triangular things. Okay, so this is contained in the parabolic group, which is the set of pairs that look like this. So this will be my P. Okay, so that is this first part. There exists a maximal parabolic containing the stabilizer. The stabilizer should contain the entire upper block. Okay, which it does, right? A12 and B12 here are arbitrary. Okay, so that's step 1. A12, B12 arbitrary gives 1. Okay. My point should be stable with respect to some subgroup here. That's not too much smaller than the original thing. Well, oh, right. And here, this was something that confused me the first time I read it. This means stable in the GIT sense, not in the stabilizer sense. Right? Okay. So is it? Well, yeah, this point, if I look at the action of GLR cross GLN minus R, or let's say it's almost stable, except I can drive it to 0 in sort of a silly way. So IR 0, 0, almost stable under the Levy subgroup, which looks like GLR, GLN minus R. Okay, except that I can do a silly thing, right? I can do epsilon times the identity and epsilon inverse times the identity. And if I do this, if I left multiply by this, okay, this is in here, but this will drive this to 0. Okay, so let's do away with that. Okay, so to do away with that, it's actually stable if I just make this SL. Okay, so this is now a reductive group, and its rank is 1 less than this Levy subgroup. So this is reductive. Delta equals 1. Okay. And then finally, we now have to ask, what is this stabilizer within this reductive group? And there we've already calculated, actually. So in here, right, what's the one condition? The one condition is this one. So instead of 2 copies of GLR, because this was really like, right, I have the left and the right part. Oh, sorry, so delta here is 2, because I had the left and the right. Okay. Right, so what's the stabilizer here? Well, instead of 2 copies of SL, I really get 1 copy because the other one has to be the inverse. So the stabilizer in L of X is like SLR GL n minus R cross, but then this thing is no longer free, right? Because this thing, if this is A11, this must be A11 inverse transpose. So my dimension of L mod this stabilizer is like R squared minus 1. Okay, and we said we want this to be big, right? So when R is big, when the rank is big, this is big. Okay, and as the rank gets smaller, this gets smaller. Okay, so in all cases, we had defect. Where did that defect go? Defect 2, because we had this silly thing that there were these zeros, and that's like the same thing in the permanent versus determinant, where it doesn't depend on all the variables, so you can drive it to 0 for like silly reasons. But you can undo that with a small defect in dimension, okay? And then what this is telling us is like, well, how many things you know, if you still depend on lots of things, then you're not sort of very far into the null cone. You're like very partially stable or partially very stable, something. Partially stable in a very good way. Okay, but so these matrices, I think this is a good example for thinking about partial stability. And then next time we'll talk about, okay, what does this look like for things like permanent versus determinant? And what are the nice properties this gets us? How that relates to these stabilizers. And then that plays into this whole story of natural proofs and P versus NP in GCT. But yeah, I will stop there for today.